Jai Hind everyone. I am Shruti Jain, Assistant Professor, MCA Department, Ajay Kumar Garg Engineering College. The topic that we are going to discuss today is the mathematical induction topic. This topic is covered under the discrete maths subject. The subject code is BMC 104 and the target students, this is mainly meant for MCA first year students. So let's understand first what mathematical induction is. Mathematical induction is, it always says that we can reach at the step 1. We start from step 1, slowly moving to step 2, step 3 and so on. We reach to a step k. So this is what we assume, that if we start from step 1, we can easily reach to the step k. The next step is to reach to the step k plus 1. Now, we can reach to the step k plus 1 only if we can reach the step k. So, when we are talking about the mathematical induction, it says that if I wish to convince that I can climb a ladder of n steps, no matter how large this n is, my strategy would be based on two rules. The first rule says that I can climb to the step 0, that is the base of the ladder. I am standing at a place there on the ground, so this is the step 0. The rule 2 says if I am on step k, I know how to climb to the step k plus 1. So if I reach to the step k over here, I can easily reach the next step, that is k plus 1. For example, if someone gives me a ladder of 3 steps, I use the rule 1 to climb to the step 0. Then when I am at the step 0, I can use the rule 2 and I can move to the next step, that is 0 plus 1, the first step. Now, when I am at the first step, I can move to the step 2 by just using the rule 2, that is, if I am at step k, I can easily reach to the step k plus 1 and so on. For now, when I have to reach the step 3, I will use the concept of the rule 2 again. I am at step 2, I will use the rule 2 and I will climb to the step 3. So here it should be clear that how I can use these two rules to climb a ladder of n steps for any n, that is regardless of its size. So here I will use the rule 1 only once when I am at the base step, and then I will keep on using the rule 2 as many times as needed. So this is the essence of the proof technique, which is known as the mathematical induction. So the principle of mathematical induction is a useful tool for proving that a certain predicate is true for all natural numbers. It cannot be used to discover the theorems, but only to prove them. We already have the theorems with us. We need to prove them only with the help of this mathematical induction. So when we talk about the regular induction, we have the 3 main steps. The base step, which talks about that I am at step 0, that is P0. The next step is the inductive step, which says that I am at k plus 1 and I am going to prove for k. I am at step k and now I am going to prove it for k plus 1. So the base case over here is P0, which we consider it to be true. Now for the inductive step, we say that for all k belonging to n, if pk exists, then pk plus 1 would be implied by pk. So pk implies pk plus 1. And hence the conclusion says that for all n belonging to n, the pn exists. That is, the proof that we wanted to do will exist, where n is a set of natural numbers. So in general layman language, we say that if we know that P0 is true and also that Pk implies Pk plus 1 for any k, then we can conclude that Pn is true for all n belonging to n. So this gives us a structure to write an induction proof. So the steps would be, the first step would be, what is a predicate? First of all, a predicate is a statement that evaluates to either true or false, usually n belonging to n, but not always. Then we'll take the base case, that is this base case where that we were talking till now. So we'll prove for the base case, which is also known as the basis step P0. There could be more than one base cases, so we need to be clear with each and every base cases if we have multiple. Once this base case is done, then we'll move on to this inductive step. For all k belonging to n, pk implies pk plus 1. So we'll prove the inductive step, which is an implication statement involving the universal quantifier. The usual rule for proving such statements apply here and should follow the following steps. For example, for any k belonging to n, we'll assume that pk is true, that is the inductive hypothesis. Then we write down the predicate pk, because earlier it was given in the form of pn, now we'll write it in the form of pk. Now we'll consider the problem of the size k plus 1, we'll break it down into smaller problems of size k. We'll apply the inductive hypothesis of the size k problem that we already have, and we'll proceed to show that pk plus 1 is true, and that would be the conclusion. If we have a non-zero base case, the base case would become p1, rest all the things will remain the same. So let's take an example. Where we need to show that the sum of first n natural numbers is n into n plus 1 by 2. The first step was to write down the predicate Pn. So Pn is 1 plus 2 plus till n is n into n plus 1 by 2. The base case will take for n equal to 0. So we'll consider it for P0. When we find out for P0, we get the value of n as 0. So on the left hand side we get 0. On the right hand side again the n becomes 0. So we get 0 into 0 plus 1, that gives us 0. So 0 equals to 0. Therefore P0 is true. The third step is to find out for Pk. We'll consider let Pk be true. So when Pk is true, we'll replace this n by k and we get 1 plus 2 plus k till k is equal to k into k plus 1 by 2. Now the next step is to prove for pk plus 1. Now when we'll do it for pk plus 1, what we need to prove is till k was already there, we'll add one more term k plus 1. So we get on the left hand side 1 plus 2 till k plus 1, and here it becomes k into k plus 1 by 2 when we had the hypothesis of pk. Now we'll replace this k by k plus 1, we'll get k plus 1. This k gets replaced by k plus 1. This k again gets replaced by k plus 1. So we have k plus 1 plus 1. So this becomes k plus 1 into k plus 2 by 2. So this is what we need to prove over here. Now how will we do that? Well, we already know that till here it is k into k plus 1 by 2. So here this is basically 1 plus 2 till k, and this is another term. Now till k we already have it as k into k plus 1 by 2. We have one more term k plus 1 added to it. So we get it like this. When we will solve this, we'll take the LCM. We'll have k into k plus 1 plus 2 into k plus 1 by 2. From here we can take k plus 1 common. So we get k plus 1 taken common from these two, and then we have k plus 2 left over, this k and this 2, and hence we reach to this solution. The other way could be, we can just open it up, we get a quadratic equation. When we'll find out the we'll find out the factors by splitting the middle term. We'll again get the two factors as k plus 1 and k plus 2 divided by 2. So this was what we needed to prove for the RHS over here. So this LHS becomes equal to RHS, hence proved. Thus we can say that pk plus 1 is true. Now pk plus 1 is true, that means by mathematical induction, the statement that was given to us in the form of n is true. Let's take another example where we have the sum of odd integers that is 1 plus 3 till 2n minus 1 is equal to n square. So we'll first assume it for the base case, we'll assume it for Pn. So Pn is the same statement for all integers n greater than equal to 1. Now here the base case would be for n equals to 1, reason being because here it says that for all the integers n greater than equal to 1. The value of n over here, we get 2 minus 1, 1 here on the left hand side. When we'll substitute the value of n on the right hand side, we get 1 square equals to 1. So we get n square equals to 1 square equals to 1, which is equal to the left hand side. And hence we get that P1 is true. The next hypothesis is, we'll consider that Pk is true. So we say that let Pk be true. When Pk is true for k belonging to n, that is the inductive step, we need to prove for Pk plus 1. So when Pk plus 1 is the case, we'll have these all things over here, and then we'll add one more term, that is 2k plus 1. How do we get this? Now we'll replace this k by k plus 1 because that would be the next term. So we'll have 2 into k plus 1 minus 1. So this becomes 2k plus 2 minus 1, which becomes 2k plus 1 as the next term. So this becomes 1 plus 3 till 2k minus 1 plus 2k plus 1. Here it is n square, so this becomes k square. When we are working for the hypothesis k plus 1, it becomes k plus 1 the whole square. Again, we'll apply the same thing. We already know that 1 plus 3 till 2k minus 1 is equal to k square. We'll replace this whole thing by k square. So as soon as we replace the whole of the thing by k square, we are left with k square plus 2k plus 1. So when we open it up, this again becomes the quadratic equation k square plus 2k plus 1, which is basically the k plus 1 the whole square. This is the expansion of k plus 1 the whole square, where in general if we talk about a plus b the whole square is equal to a square plus 2ab plus b square. So when we replace this a by k and this b by 1, we get k plus 1 the whole square as k square plus 2k plus 1. This was what we needed when we were, this already we got in the RHS. The conclusion of LHS is equal to the RHS, which is k plus 1 the whole square. Thus Pk plus 1 is true. The statement that was given to us is also true. Let's take one more example where we talk about 7 to the power n minus 2 to the power n is divisible by 5. Now this again is for all the integers greater than equal to n. So let's consider the case for Pn, then we'll consider it for base case, that is n equals to 1. When we substitute n equals to 1, we get 7 to the power 1 minus 2 to the power 1, that is 7 minus 2, that is 5. 5 is divisible by 5 and hence the base case is true. That is P1 is true. Now the inductive step, which says that let's assume it to be true for Pk. When it would be true for Pk, where k belongs to the integers, we get the Pk as 7k minus 2 to the 7 to the power k minus 2 to the power k is divisible by 5. Now the next step, we need to prove it for Pk plus 1. When we say that it is divisible by 5, we cannot prove it in that manner because we need some equation to be true when we are solving any of the hypothesis. So what we say that 7 to the power k minus 2 to the power k is equal to 5 into a, where a is any integer by definition. Because if I take a as 1 and k as 1, so I get 5 is equal to 5. Similarly, when I take k equals to 2, I get 7 square, that is 49, minus 2 square, that is again 4. So 49 minus 4 becomes 45, that is 5 into something multiplied. So 5 times 9. So this a over here becomes 9. So 7 to the power k minus 2 to the power k is equal to 5 multiplied by some factor of it, that is again an integer. Now let's consider the case pk plus 1. Now when we need to prove it for pk plus 1, what we basically have to prove is that 7 to the power k plus 1 minus 2 to the power k plus 1 is divisible by 5. When it is divisible by 5, again it means that we need to show it for something multiplied by 5. So we'll try to break it in that manner. Now 7 to the power k plus 1 is 7 into 7 to the power k, because we know by definition that a to the power m plus n is always equal to a to the power m into a to the power n. So using this definition, 7 to the power k plus 1 is basically 7 into 7 to the power k minus 2 into 2 to the power k. Now this 7 that we are talking about, this 7 can further be broken down into 5 plus 2. That means 7 into 7 to the power k is basically 5 plus 2 into 7 to the power k. Why are we doing it? Because we need to get something that is related to either 2 or related to 5, because we need it as a factor of 5. That is why we have broken this 7 into 5 plus 2. When we break it up, open up the bracket, we get 5 into 7 to the power k plus 2 into 7 to the power k, followed by this one as it is, minus 2 into 2 to the power k. Now if we look over here, we keep it as it is. From here we take 2 common, we get 7 to the power k minus 2 to the power k, and by definition we already know that this is equal to 5a. We already have taken it for pk. So this becomes 5 into a. This becomes 5 into a, which is 2 into, this is 5 into 7 to the power k. If we take out 5 common from here, what do we get? We get 7 to the power k plus 2 into a. That is again 5 into some multiple. Let's assume it as a, or let's assume it as capital A. Thus, it becomes a multiple of 5, right? Because it is multiplied by 5. Anything multiplied by 5 becomes a multiple of 5. Hence, pk plus 1 is true. So, we say that by mathematical induction, this is true. So, what we have done over here is, we took it for Pn, because it is for all integers n greater than equal to 1, we considered it, when we considered it for n equals to 1, we substituted the values and we got the value as 5, which is divisible by 5. Then we assumed pk to be true. When pk was true, because we are not getting it in the form of an equation, we made it equal to 5a, because 5 multiplied by anything gives us the result as the multiple of 5 only. Once we did it, we considered the case pk plus 1. When we considered the case pk plus 1, we replaced 7 to the power k by 7 to the power k plus 1 minus 2 to the power k plus 1. Now, by the definition, we know that a to the power m plus n is equal to a to the power m into a to the power n. Using this definition, we got 7 to the power k plus 1 is equal to 7 to the power k, 7 to the power k into 7. Further, we divided this 7 into 5 plus 2 because we needed two things. The first one was something to be a multiple of 5, something to be a multiple of 5 and something to be related to 2 over here. So, we broke this 7 into 5 plus 2. We opened the bracket. So, this 7 became 5 plus 2 into 7 to the power k. So, this becomes 5 into 7 to the power k plus 2 into 7 to the power k, and we took this 2 into 2 to the power k from here. We combined these two, took 2 common, we get 7 to the power k minus 2 to the power k. We already know that 7 to the power k minus 2 to the power k is 5a. We substituted this to, we substituted the value 5 Instead of 7 to the power k minus 2 to the power k, we substituted it as 5a. Now, this has 5, this has 5. We took 5 common. 5 multiplied by anything becomes a multiple of 5. And hence, the 7 to the power k plus 1 minus 2 to the power k plus 1 is divisible by 5, which says that pk plus 1 is true. Once pk plus 1 is true, we say that by mathematical induction, the statement is true. So that's all for today. Thank you.